Hi everyone, welcome back to my channel. In today's video, we're going to talk about some of the concepts of probability that are going to be very helpful in solving some of the brain teasers that are going to come ahead in the near future. If you're first time to my channel, my name is Prakash Duhoon, and I currently work as an independent money manager and also as a career coach. Okay, so what are we going to talk about in today's video? We're going to talk about a bunch of probability-based theorems, the formulas, including conditional probabilities, total probability formulas, and we can then move into something what we call as a Markov chains. Now, what you would see is a lot of quant problems. They can be tough probability-based problems. But when you start applying concepts like advanced concepts like Markov chains that are again based on probability, these problems become very easy to solve. And we're going to see some of that in the upcoming videos. So I hope you pay a lot of attention to this video especially, and watch it till the end, because it's going to make your understanding of the upcoming videos very easy. Okay, so stay tuned till the end and see you. Okay, so let's start, and we'll start with some basic definitions, and then we can move on to more formulas. So I'll start with some basic definitions, starting with sample space. Sample space basically means the set of all possible outcomes. Okay, so let's say if you toss the coin, there can be two outcomes, heads or tail. And for two coin toss, I'm going to talk about that shortly. So it's basically a set of all possible outcomes. It's denoted by a symbol called omega. And let's talk about some examples. So let's say if you have one coin toss, omega in this case is going to be heads and tails, because these are the only two possible outcomes or occurrences that you would see if you toss a fair coin, or even if it's a biased coin, doesn't matter. They're just two sides, one is head, the other is tail. And let's say if there was two coin toss. So if you have two coins, we're tossing them simultaneously. Omega here is going to be heads, 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 tails, tails, heads, and tails, tails. Okay? All right. So now let's move to the next definition, which is an outcome. So we talked about possible outcomes here, but what is an outcome? So outcome is basically one of these occurrences. So heads, heads, or heads, tails. This is nothing but an outcome. So like I mentioned, this is one of the possible outcomes, okay? An example could be here is, let's say, heads, tails in a two coin toss. And it can be denoted by different symbols, but here the symbol we use is this. So now let's move to the next definition, which is an event. So event is nothing but a subset of sample space. Okay, so if you remember, the sample space in a two coin toss is like this, as we can see on the screen. And if you have a subset of these, this is a set and it has 4 elements. So you can find all the possible subsets, and any subset of this sample space is going to be an event. Example could be, say, I define an event A as obtaining. So this is an example, obtaining one head in two coin toss. So we were saying we toss two coins and we want to find out outcomes in which, the outcomes in which you have one head, only one head out of the two coins. So as you can see, the possible outcomes that are going to be contained in A is going to be heads, tails, or tails, heads, because these are the two occurrences where you have one head. In the other two, as you can see, one contains two heads and the other one contains 0 heads. Okay, so we're focusing on these two. All right, so now let's talk about some formulas. So what is probability of any event A? So A is basically an event. The probability is nothing but the total number of favorable outcomes upon all possible outcomes. Okay, so what I mean to say is probability of A happening. When I say probability of A, that basically means probability event A happens So we find out all the possible outcomes in which A occurs, and then we divide it by all the possible outcomes which exist in this world in which we are dealing in. So basically, this is going to be sample space. So if I talk about an example, let's say in our case, we had A event was obtaining one head from 2 coin toss, okay? And probability of A is going to be, we're talking about total number of favorable events. So if we go back, we saw in this case, we had 2 events here, and the sample space consisted of 4 events. So this is going to be 2 by 4. That's going to be half, okay? And if you're thinking this is way too easy, just hold on for a second. We're going to start moving to more complicated stuff shortly, but I just want to make it, really comprehensive so that it's like a crash course, okay? So that if you have an interview coming up, you can just review this video and, you can be really come up to speed. Okay, so by definition, probability of an event has to lie between 0 and 1, okay? So if it's a 0 event, that basically means, if it's 0, this means it's an impossible event. And if it's a 1, you can call it as a sure event. Okay, and this sign is basically if and only if. That what it means is if I say an event A is impossible, this means the probability of A happening is 0. And if I say probability of A is 0, this means it's an impossible event. Okay, so this is an both way implying sign, which we also call it by if and only if. So this is if and only if. And you may have heard about this probably in some of your textbooks, or probably if you were ever reviewing any kind of a quantitative problem. All right. So now there are a few more notations which you might encounter, and some of them are like this. So let's say if A is an event A, and so let's say A is an event, then we call something called as A bar or A complement, which is basically A not happening. This basically means A not happening. And A means basically A happening, event A happening. Okay? So if you have to note it like this is how you can look at it. Now, by definition, if we know a probability of an event A happening, then we can also compute the probability of a event A not happening like this. Because if you talk about any event, let's say A, and then, or let me change an event here. So let's say there's an event E here, okay? And it's a different event. So if we know the probability of E is, let's say, X, and by definition, X has to lie between 0 to 1, then probability of E not happening is going to be equal to 1 minus X. And you could also think like this: probability of E plus probability of E not happening is going to be 1. What it means is, let's say if you have any event you take, if you know the probability of that event happening, and there can be 2 possibilities, right? Either the event happens or it doesn't happen, right? There can be no other possibility. It can be like event is happening, it's also not happening. It happens or it doesn't happen, okay? And if you look at these 2 possibilities, there's a big or here, right? So A is happening or A is not happening, as you can see here. Okay, and as you may see, or basically means you get out of the probabilities if there is no intersection between them. And this will become clear, but it may be very intuitive to understand if you have any event, if either it happens or it doesn't happen. And if you sum up the probabilities, it should sum up to 1. Okay, so this is a simple formulation, and we can use it a lot of time. And how we use it is basically like this. We don't, sometimes it's easier to, if it's harder to compute, let's say, probability of event E, then we would just compute a probability of event not happening, and then we can use this relation to compute the probability of event happening. What I mean to say is like this. So if you can compute, let's say, probability of event E bar, it's easier to compute, then you can compute the probability of event E like this. And some of the problems, I think one of the problems we did, I've discussed before, we did something like this where we computed the probability of event not happening, and then we computed the probability of event E using this formula. Now let's move on to some other things. And many of the times what you would see is in your questions, you will have, let's say, different events, and we want to compute the probability of, let's say, 2 events happening. And there could be wordings like either one happens or other happens. So let's say there's an event A and there's another event B, okay? And we want to figure out if A happens or B happens, what is the probability of this, right? So first thing is to understand this is nothing but equal to A union B in terms of set theory, right? So if we had all the possible favorable outcomes for A, that is when A happens, and also the favorable outcomes for B when B happens, then we can compute the favorable outcomes for A or B, or A union B, using the set theory. We just compute the union and we get it. More precisely, let's say if A event A was this, event B was this, then you can compute the union quite easily, and the union is got to be basically all the common areas, including the common areas and also the non-common areas between the two sets. Okay, so the highlighted section is basically what you call as the A union B. Okay, and similarly, if let's say you have A and B, that basically means both the events have to happen at the same time. So this is, in set theory, it becomes A intersection B. And I'm assuming at this point of time you understand basic set theory, but if not, I would highly recommend you check it out, some of the resources, and refresh them if it's a bit rusty. Okay, and some of the natural things, as you can see, is A union B is actually equal to B union A. And if I draw the intersection diagram, this is going to be, this is A intersection B, and this has got to be equal to B intersection A. Okay, so these is again important formulas. Now let's talk about independent events. So let's say there are two events. Again, event A, event B. So A and B are independent. If they're independent, basically that means the probability of A and B happening together is going to be equal to probability of A times probability of B. Okay, so let me give an example. For example, let's say A is heads on a fair coin toss. That's event A, and event B is raining on that day. So there are two events. One is basically you toss a fair coin on a given day, and also the probability it rains on that day. Okay, and by all practical means, it's got to be independent. They don't really affect each other. And so if I had to compute the probability of A intersection B, that basically means A and B happening on both day. That is, if I toss a coin and I get ahead, the probability it rains on that day, they're going to be independent. So it is nothing but probability of A times probability of B. That is, what is usually the probability that it rains on a given day times the probability you get ahead. These are basically that's the basic formula of independent events. Okay, so I'll quickly talk about now some of the formulas, and then we can also see how independent events influence these formulas. So one of the formulas which you would see is, let's say if there are two events again, event A, event B, the probability of A union B. And right now, I don't claim anything about their independence or their non-independence, but probability of any two events happening, this is A or B, which is equal to saying A union B. Then probability of A union B is nothing but probability of A plus probability of B minus probability of A intersection B. Okay, so this is a generic formula for any two events. If they have to, either one of them has to happen or both. A or B means one happening, A happening or B happening, or both of them happen, right? So this is nothing but probability of A plus probability of B minus probability of A intersection B. All right. And if I quickly go back to this diagram, I can probably talk about how this formula has come up. So if you look at this, probability of A is going to be computed from this diagram, and the probability of B is going to be computed from this diagram, okay? But you see there are two, this area gets counted twice. That's why there's a subtraction that happens here with the intersection. Okay, now let's also quickly apply how if A and B were independent, how this formula would change. Okay, so if A and B are independent, so then this formula would become A or B happening is going to be equal to probability of A plus probability of B minus probability of A intersection B. That's going to become equal to probability of A times probability of B, right? And how did I come up with? If you look at this formula here, which we had just shared about independent events, you could just go and apply this all the way here. It gets applied here. So you get probability of A plus probability of B minus probability of A times probability of B. Okay, Now let's do a quick example and also get an understanding of this formula, how it's applied. Okay, so let's say we have two coin toss. Okay, and the first event is the first coin gets head, and H is basically heads here. Okay, and T, by as you may have thought, it's tails. And event B is second coin gets heads. Okay, so what we're doing is we're saying on a two coin toss game, we are defining two events. One is the first coin gets ahead and the second coin gets ahead. Okay, and you may have two coins. I'm just calling this one. This is second coin. This is coin one. This is coin two. Okay, and then I am talking about. Now I want to find out the probability of A union B. Okay, or this is nothing but probability of A or B happening. So what I'm saying is we want to find out the probability of this new event, which is either the first coin gets ahead or the second coin gets ahead. And when I say A or B logically means either A is true or B is true or both is true. Okay, so let's first try to compute this using the formula, and then we'll try to also understand if this is intuitively it's also true. Okay, so probability of A or B is probability of A union B is probability of A plus probability of B minus probability of A intersection B. Okay, so because they're fair, I'm assuming these are fair coins. They're fair coins. So probability of head on a given fair coin is going to be half, and because both are fair, so it's going to be half for coin B as well. But this A intersection B means that you get a head on both the coins. Okay, so this basically means is you get a head-head situation. And as you may have thought about it, this means that probability of half times half, because now these are two coins and they're independent. One coin toss is not going to affect other, right? So I can also say here that probability of A intersection B is probability of A times probability of B. Okay, and we can apply this independence here. So suddenly now we see it becomes easier. So now it's 1 minus 1 over 4, which is 3 by 4. Okay, so this is the probability we have. Now let's try to also understand intuitively this is true. So if you remember, the sample space for two coin toss was heads heads, heads tails, tails heads, and tails tails. Okay, and our event is A gets heads, the first coin gets head, and the second is second coin gets head. Okay, and C is basically a coin here. Okay, now if you see what are the possible events in which A or B is happening. Now A or B means, like I just showed you, A or B implies either A is true or B is true or both. Okay, and here what it means is the first coin gets ahead. When is it true? This is true. The second coin gets ahead. This is also true. Second coin gets ahead. This is true. This is true here. And both of them get ahead. That's also fine. This is covered here. So you have this case covered here, this case covered here, and this case covered here. This is the only case which is not satisfying this, because none of the coins here have a head, neither A nor B. So as you can see, there are 3 favorable outcomes, and their total outcomes is 4. So the probability using the basic formula that we had computed was also, if I say A union B, here is also favorable outcomes, total number of them upon total outcomes. Okay, so here you have 3 by 4. So using this understanding of sample space, because it's a smaller example, you can also confirm that the formula actually works fine. But it's going to be helpful for more complicated cases.